Okay. Hello everyone, welcome to my course Introduction to Market Structures. So, we were doing entry deterrence model and specifically we were doing the Dixit model. So, in the last class we have derived the reaction function of farm 1 and the reaction function of farm 2 given that farm 2 enters. Now, farm 1 here is the incumbent farm. So, it can invest in its capacity which is same as the capital, and farm 2 is an entrant farm and it enters if it is profitable for that farm to enter. If its profit is 0 if it enters, then that farm does not enter. Okay. So, today we are going to solve this problem and we are going to solve this assuming a general downward sloping demand curve. Okay. Suppose we assume that the farm 2 suppose enters. Okay. So, farm 2 enters. Okay. So, when it enters we know there is Cournot competition. Okay. So, based on that we will get that there are Cournot reaction functions, but the reaction function of farm 1 is going to be slightly different than the usual Cournot reaction function that we have done while doing the Cournot oligopoly or Cournot duopoly. But for farm 2 it is going to be same as the Cournot reaction. Okay. Now, further farm 2 decides its capacity and capital at the same time. Okay. So, it is this. So, it means that when it is deciding its output at the same time it is deciding the amount of capacity it wants to have. So, it will never going to have capacity more than its output. So, if it is more, so if suppose capacity is this and it produces some amount this and this amount is suppose positive, then the cost on this excess capacity is this much. So, it is not getting any return on this excess capacity. So, that is why it is not optimal strategy for farm 2 to have a capacity higher than its output. So, that is why K2 is always going to be equal to Q2, that is output of farm 2, and marginal cost function of farm 2 is this, because it decides its capacity and the labor at the same time. So, and since suppose we assume that the demand curve is linear, then we get the reaction function of farm 2 in this form. Why do we get this? Because we take the profit function of farm 2 can be written in this form. This is suppose the demand curve or demand function output of farm 2. So, this is the total revenue, this is the total cost for on production and the cost for entry is this. So, this is the profit, and if we take the derivative with respect to Q2 we get this reaction function. Okay, and we denote it in this way, which is a function of Q1 output of farm 1. Okay. And reaction function of farm 1, suppose there is a K1 capacity which is an arbitrary number. Okay, in stage 1, then the reaction function of farm 1 in stage 2 it is given like this. This is the case when Q1 is less than K1. So, when it is producing less than its capacity, then it requires marginal cost is only this. So, when Q1 is less than this, less than equal to this, marginal cost is only W, and when Q1 is greater than this, then the marginal cost is this, right, because it has to now expand its capacity. So, that is why from there we get this, and we have done it in detail in the last class. Okay. Now, we will denote some specific outputs and our analysis will be based on those outputs. Suppose this is the output of farm 1, output of farm 2, and this is the reaction function of farm 2. Okay. this is now here you can look at, suppose the demand curve is this, demand curve. So, let us write here, suppose demand curve is this. Okay. Then we get this, this is the profit function and reaction function of form 2. It is this. So, it is this line and the reaction function of form 1 like this. So, this is what? This, it is this. This is the reaction function if it is this, suppose some k is big enough. So, we get this and the reaction function if output is greater than is this, then so it will be because it will be producing till its K1 based on this capacity, it will be this in the additional amount will be based on the, so the marginal cost is this, not the total cost. So, total cost for it, because it has already incurred this much cost, this in stage 1, right. So, it will be this one and so the reaction function of form 1 is so it is something, suppose this and this reaction function is this of form 1. Now, this is the symmetric output because this is the reaction function and this is the reaction function. So, we take this point to be the point T and this is this asymmetric thing. This point is V and this is V. This is the Coulomb outcome when we have reaction function is this. And if from here now if we can have K here and the reaction function of form 1 is this, if K is here then the reaction function is like this. Okay, we have done that. Now, what do we can see here? This is the point T, this is point V. So, we can have the reaction function of form 1 if this is K1 then the reaction function is this green line. We may have a situation like this, if suppose this is K1 then this light blue line is the reaction function of farm 1, and if this is K1, then the red line is the reaction function of farm 1. And we will do the, so the reaction functions are of this nature, and we will now see that what is the outcome in stage 2. Why we are looking at stage 2? Because it is a 2-stage game, and in a 2-stage game we look at subgame perfect Nash equilibrium, and in subgame perfect Nash equilibrium we solved it using backward induction. So, we will first solve the stage 2, assuming that suppose farm 2 enters, because moment farm 2 enters there is Cournot competition, and we have defined the reaction functions of farm 1 and farm 2 here. Now, first in the stage 2 we may have a situation where farm 1 needs to expand its capacity. When do we see that? Suppose this is the outcome. This is Q1, Q2. This is the reaction function of farm 2. Okay. This point is V, this point is T, and suppose K is here. So, the reaction function of farm 1 is this thick blue line. Okay. Now, if this is the reaction function of farm 1 and the reaction function of farm 2 is this, then they intersect at this point. So, the outcome in stage 2 is this. So, this point. So, this is the outcome in Cournot competition, right. So, if this is the outcome in Cournot competition, because this is the reaction function of farm 1, okay, this line, this kink line. So, they intersect here. So, what is the output of farm 1? Output of farm 1 is this, output of farm 2 is this, capacity of farm 1 is K1. So, this much amount it has to expand. So, this much is amount of capacity expansion by farm 1, okay, in this situation. Because this is the reaction function of farm 1 and this is the reaction function of farm 2, they intersect here. So, this point is the Cournot outcome, Cournot quantity competition outcome. So, the output of farm 1 is this, output of farm 2 is this, and here this much, this is greater than the capacity of farm 1. So, it will lead to an capacity expansion by farm 1. Okay. So, in this what happens, if K1 is less than this output Q1T, then we see that there is capacity expansion by farm 1. This is the outcome in this kind of scenario when the capacity of farm 1 is not sufficient. Now, when we have excess capacity, farm 1 may have a situation where it has excess capacity. When? So, this is suppose the reaction function of farm 2. So, this point is T and this point is V. We know these points. Okay. Now, suppose the capacity of farm 1 is here, K1. What is the reaction function of farm 1? Reaction function of farm 1 is this thick blue line, kink at this point, and reaction function of form 2 is this. So, this point is the outcome in Cournot competition. Now, if this is the outcome in Cournot competition, what is the output? This is the output of form 2, this is the output of form 1. Okay? Capacity is this much. So, this much is the excess capacity K1. This should be small k, okay? Q1V. So, this is the amount of excess capacity. Now, what is the cost in this? This is, you can say, this is equal to sunk cost, because form 1 is not going to get any return on this. So, form 1 will never want to have this unnecessary cost, because it is not getting any return for this. So, that is why here we get that the K1 should always be less than equal to Q1V. This is the outcome. And here this is the excess capacity, and when do we get excess capacity? When K1 is greater than Q1V. So, if K1 is greater than this output of this much level of output of form 1, then there is excess capacity, right? We get this. Now, when this is one outcome, and form 1 will never want to have excess capacity here, because if it has, then it is a sunk cost for it. This much amount of cost is, it is not getting any return on it, it is unnecessary, because if it has this, then also the outcome is this. Okay? If capacity is here is equal to this, outcome is same. So, this much cost is unnecessary. Next, let us look at when there is full utilization of capacity. Suppose this is the reaction function of form 2. Is the T and this is V, okay, as we have already defined. Okay. Now, suppose capacity is here. So, the reaction function of form 2(1) is going to be of this thick blue line, this, and where do they intersect? They intersect at this point. So, this is the outcome in Cournot competition. If this is the outcome, then what is the output of form 2? Form 2 produces this much and form 1 produces this K1. So, Q1 is equal to this, and this is Q star, where Q star is greater than this much amount Q1V, sorry, and it is less than this in this situation, okay, an output of this. So, here you can take any, if you look at this, any point here, K, here it will be like this only, here it will be like this. So, if K lies within this range, then full capacity by farm 1. Okay. So, we have seen that in stage 2, suppose farm 2 enters, then what are the possible outcomes depending on the capacity of farm 1. So, if capacity is very low like this, then the farm 1 needs to expand its capacity and the outcome is at this point, T point. If capacity is too much, then the outcome is at when farm 2 enters is at V and the farm 1 has some excess capacity. If the capacity of farm 2 lies within this range, then the outcome is at this point which lies in between T and V, and there is full utilization of capacity. Okay. So, these are the 3 possible outcomes when farm 2 enters in stage 2. Okay. Now, we will move to stage 1, but before moving stage 1, what we will do? We will define certain outputs of farm 1, because based on those outputs we are going to decide the optimal amount of capacity chosen by farm 1. So, let us look at this. This is the reaction function of farm 2. This is the point T and this is the point V. Okay. Now, this is the output of farm 2, which is Q1T, this is Q1V. Suppose capacity is somewhere here and we get a, suppose let us draw the reaction function by this green line. This is the green is the reaction function of farm and this is the reaction function. Okay. Now, here this output is Q1M, this is the monopoly output of farm 1. Okay. And in this monopoly outcome, what do we have? The profit of farm 1, you can write this here, this much is going to be the output. So, we will require this Q1 this much amount of capacity also. So, we can write it in this way and this is the monopoly profit. Okay. Now, here this thing given or instead of this we can write it in such a way that keep this same. Where K1 is equal to this. Okay. This will also give me this point. Okay. Because then the reaction function is going to be this point. Okay. And so, this is going to be the monopoly outcome. Now, we are going to also have another, that is output, that is this Q1L, and this is the limit output. We have already defined what do we mean by limit output, because we can write this profit of farm 2 can be written as a function of, because we can write this So, this function, this is actually a function of Q1. We can write it. If we plug in the reaction function, we get this. Now, if this Q1 is equal to a output which is Q1L, the limit output, then it is this. So, that is why this is called the limit output of farm 1. If farm 1 produces this output, profit of farm 2 is going to be 0. We have to incorporate the entry cost also, and the entry cost is F here. Okay. Next, we define another output, and that is the Stackelberg output of farm 1. Now, these outputs Q1M, Q1L, Q1T, Q1V, all these can be of different values, and we can rank them also, and depending on their ranking we will get the outcome in stage 1. Okay. So, this is output of farm 1, output of farm 2, this is the reaction function of farm 2. Let us draw it like this. This is point T, this is point V, this is Q1M, and we know these are the isoprofit function, oh sorry, here when we are drawing it, it is isoprofit curves of farm 1 if its reaction function, if its marginal cost is, if MC is equal to W plus R, right. And you will see it is in fact MC, because otherwise because there is no point in having excess capacity. We have seen that in capacity greater than this output, right. So, we may have a situation, oh sorry, it is not we may have, we will have a situation where, so it will, the capacity will be such that it is going to produce that much amount, it will never have excess capacity. Okay. So, if it does not have excess capacity, then it means then this portion, this the at the optimal point, this is equal to this, if we are always going to have full utilization. Okay, and we will see that we will always have full utilization. Okay. So, that is why we are taking this as the isoprofit curves rather than taking from here. Now, again we will have this, and we may have a Stackelberg outcome like this. This is the Stackelberg outcome of farm 1, because at Q1S isoprofit curve of farm 1 is tangent to the reaction function of farm 2. We have this. So, we will get some profit, and suppose this profit of farm is this Stackelberg represented in this way. Then each point in this isoprofit curve will give me this, because isoprofit curves means all the combination of output of farm 1 and output of farm 2, so that the profit level of profit is fixed. So, we will have a output here also. So, at Q1S naught, profit of farm 1 is same as the Stackelberg output, but Q2 is equal to 0. Okay, this. We will also require this output, because see, this profit at this point is same as profit at this point. Now, here you can see that if we take a isoprofit curve like this, and suppose we look at this point, then this point lies above this isoprofit curve. So, the profit here is going to be less than this profit. Okay? If that is the case, then we would prefer this Stackelberg rather than this, right. And here we will use this to, in certain situation, to determine whether what kind of optimal capacity the farm 1 should have. Okay. That is why we require this output and this Stackelberg thing. Okay. So, I hope it is clear. So, we have defined these outputs Q1T, Q1L, Q1M, Q1S, Q1S0 and Q1V. Okay. And all our analysis, further analysis will be based on these outputs. Okay. So, I hope it is now clear the definition of these outputs of farm 1. Okay. So, this point is giving me Q1T, this point is giving me Q1V, this point is giving me Q1M. Q1S is given by this point where isoprofit curve of farm 1 is tangent to the reaction function of farm 2, and Q1S0 is given by this point where the output of farm 2 is 0, but the profit of farm 1 is same as the Stackelberg output, or where this profit level on this. Yeah, it could have been this point also, not, but we have taken this, because this is also a point where profit is same as this level, but output of farm 2 is 0, but we have taken the higher one, this one. So, remember this. Okay. Out of these two profit, these two outputs, we have taken this and not this. Okay. Now, let us look at stage 1. So, in stage 1, let us look at this situation where profit of farm 2 at point T is 0, is negative, and the profit of farm 2 at point V is also negative. So, if this is the reaction function of farm 2, and this is point V and this is point T, then profit of farm 2 at T is negative, profit of farm 2 at V is negative. And we know at Q1L profit of farm 2 is equal to 0. So, this implies, Q1, this is what? Q1T, this is Q1V. So, Q1T implies that Q1L is actually less than Q1T. So, Q1L is somewhere here, then only the profit at this is going to be negative of farm 2. So, we will see what is the best thing to do here. So, in this case, when case 1 we have got this is suppose the reaction function of farm 2 So, farm 1 while doing this calculation in stage 1 while deciding K1, it will see that profit of farm 2 here is 0 at T. Again this is also 0 at V, right. So, now suppose the capacity is here. So, the reaction function is this, and if farm 2 enters, the outcome is this, right, if farm 2 enters, but here profit is negative. So, farm 2 will not enter. So, since profit is negative at T, that is this. So, farm 2 never enters here, whatever, because if the capacity is here, then reaction outcome should be this, but since profit is negative here, it will be negative here also, it will be negative, and since it is negative here also. Okay. So, what do we get in this situation? Because see, if we look at this reaction function of farm 2, isoprofit curves are somewhere here. So, this is the monopoly, right. So, profits are decreasing like this. If it is negative here, then it will be negative here also, right. So, that is why it is, even if capacity is here, reaction function is this, farm 2 enters, output is this in stage 2, it will earn negative profit. So, it is better not to enter and earn 0. So, here in this situation, output of farm 1 is going to be this one, this monopoly output, because farm 2 never enters. So, farm 1 will not be threatened by the entry of farm 1. So, because even if it gives a signal that I am going to enter, it is not going to threaten farm 1, because farm 1 knows that farm 2 is not going to enter. So, in this situation, we get a thing that K1 is always going to be of this much amount, monopoly amount, and farm 2 never enters. So, if this is the reaction function of farm 2, is going to, it will and this is going to be the outcome. Okay. So, optimal K1 is this, or even if it is anything, it will never going to be, because if suppose the K is this, the reaction function is this, so this point is T, so it is profit is 0, negative, so it is not profitable to enter. So, you can write K1 can lie between 0 and this, and the outcome is this, and farm 2 never enters, and so this case is called something called a blockaded monopoly. Farm 1 produces monopoly output and still farm 2 does not enter. So, it gets the monopoly profit. Why? Because the entry cost is, you can think in such that if it enters, farm 2 earns a negative profit. Okay? So, that is the reason. Next, look at the case when farm 2's profit at point T is positive and also at point V it is positive. So, this is output of firm 2. So, this curve is the reaction function of. So, this point is T and this point is V. So, here also profit of positive at this point, positive at this point. So, this means, this implies that Q1L is greater than this output. So, Q1L is somewhere here. So, if this is the thing, then what should the farm 1 do in stage 1? Because while in stage 1, farm 1 while deciding K1, it will do this calculation, it will see. So, it will know that in this point also farm 2 is making positive profit in this too. So, it is making positive profit, okay, because the Q1L is somewhere here, limit output is greater than Q1V. And we know that if suppose the capacity is here, so we will do that thing. So, we will have two situations now. 2A. Suppose the case is this, Q1S is greater than Q1V . Have this Q1, Q2, okay, we have this up. And suppose this is Q1L, this is Q1V, and suppose this is Q1S. So, it is somewhere here. This is the Stackelberg thing. Okay, we have this. Now, if K1 is equal to Q1S, so capacity is this. So, this green line gives me the capacity. Then what is going to be the reaction function of farm 1? It is going to be this and this. So, if this, then in stage 2, because it knows the outcome is this, profit is stage 2, outcome is at point V and profit of farm 2 at V is positive. So, farm 2 enters and the output of farm 1 is Q1V, output of farm 2 is Q2V. Now, this much it is going to get as a sunk cost. So, if this is the situation, then what is the, so this here minus is the sunk cost for farm 1. So, here optimal capacity is, so optimal capacity is V. So, when K1 is this and farm 1 accommodates the entry of farm 2, and the outcome that we get is and this is the outcome. Okay. So, in this case farm 1 accommodates the entry. Now, let us look at this situation. Situation is, this is always going to be the case and this is going to be the case. This is Q1S. Okay. Now, here if K1 is equal to Q1V following from the previous case. So, this is 2B. Okay. Then if this is, so this is the outcome, right, we get here. And since this is the Stackelberg output, so that it is somewhere isoprofit is tangent here. So, this point V lies in an isoprofit curve which lies above the isoprofit curve passing through Stackelberg outcome, this point, then this. So, profit of farm 1 at phi is less than profit of farm 1 at this point. Suppose this is S. So, if now because of this, if K1 is equal to Q1S, this capacity is this. So, outcome is here, this is the outcome in Cournot competition, full capacity utilization, or this is the third case. If this, then full capacity utilization. So, profit will be at a higher rate, this, if K1 is this. So, if K1 is equal to this, then the outcome in Cournot competition is Q1 is equal to K1, which is equal to Q1S, and Q2 is this Stackelberg output, this Q1 star. So, here profit will be higher than this point. So, but if it produces less, if its capacity is less here, So, the reaction function will be this. So, again it will be at a isoprofit which is higher than this, because it is at this point it is not tangent. So, that is why it is optimal for. So, form 1 again accommodates form 2 and K1 is equal to the Stackelberg, this, and the outcome that we get is something like this. Okay, so the reaction function is going to be this. So, they intersect. This is the outcome in Cournot computation. Okay. So, in case 2 we see the form 2, form 1 always accommodates. It cannot deter the entry of form 2. In case 1, what we have seen, that the form 2 never enters blockaded monopoly. In case 2, when the profit at this point and this point both are positive, that is profit at T and profit at V are positive, that means the limit output is more than Q1 V, that means it is greater than Q1 V, then we have form 1 always accommodates the entry of form 2. Now, let us look at case 3. In case 3, we have a situation where we get this outcome, that suppose this is the reaction function of form 2, this is point T, this is point V. Okay. Now, profit here of form 2, this is positive. Profit here of form 2, it is negative. So, this implies that Q1L is less than Q1V, this, and it is greater than Q1T. So, Q1L limit output lies in this range. Okay. Now, what are the possible outcome in this situation? So, let us look at the first outcome. This is suppose 3A. Here, if this is less than monopoly output of form 1, Q1, Q2, okay. This is point T, this is point V, and this is the Q1M. Now, here Q1L lies here, somewhere here, suppose it is at this point. Okay. So, here this is suppose Q1L, this point is. Now, if here K1 is equal to suppose T is this. So, then the reaction function is something like this, given by this green line is going to be like this, and at this point, so it means form 2 will enter, because at this profit is positive form 2. So, this is not optimal, it does not deter. But here if Q1 K1 is this, is suppose this much, outcome, if form 2 enters, then outcome will be this, form 1's output is this. So, here profit of form 2 is equal to 0 at this C. So, then this is will deter the entry of firm 2. Firm 2 will not enter because it is earning 0 profit. So, the actual outcome is of firm 1 is going to be this. So, in this situation, and if it produces K1 is suppose is equal to M this much, reaction function will be this. Actually, the output is this, because if capacity is more than this, if capacity is more than this, then firm 1 monopoly output, then it will always, then firm 2 does not enter. If it does not enter, then what is going to happen? It means firm 1 has deterred the entry. So, K1 lying in any point here in this range, this K1 lying in this range, it deters the entry of firm 2, and this is also a situation of something like blockaded monopoly, because firm 1 has producing what? Firm 1 is producing monopoly output, and but still it is blocking the entry, it is deterring the entry of firm 2, right. So, whenever this limit output is less than this and this is greater than this, then we have blockaded, again we have blockaded monopoly, and Q1 is equal to Q1M, or it is anywhere here K1 and less than equal to Q1. If this is the situation, then it deters the entry of firm 1, deters the entry of firm 2. Okay, I hope this is clear. Next, let us do another situation, and this is suppose case 3. So, in case 3b, we will this is the reaction function of firm 2. So, this is point T and this is point P, and this is Q1S. So, here Q1L is greater than Q1M, because we have already taken when it is less in the previous case, and this is Q1S naught. Okay. This point, and Q1L is suppose greater than Q1S naught. Okay. So, it is this point is Q1L. So, this in case B, what we have taken, this is greater than Q1S greater than Q1S naught, and this is greater than Q1L. Okay. This is. Now, here if suppose it blocks the entry, how it can block? Let us do one. Let us draw this curve slightly like this, so that this point is phi. Okay. So, this is Q1L. In earlier one Q, so Q1L is less than Q1V. This has to be satisfied. This point is Q1V. So, here if this is the situation, then what do we get? It can block because this is A. So, if K1 is equal to Q1L, then it is going to do what? We will get this reaction function, and then profit of form 2 is 0. So, outcome is, this is the reaction function of form 1, right. So, form 2 doesn't enters, form 2 doesn't enter, and reaction function is this. So, outcome is this. So, this is the profit point of form 1, this, when it produces K1 is equal to K1, this. But suppose, and this is the profit if output of form 2 is 0 and form 1 is getting the Stackelberg profit, then the profit is here. This is the monopoly profit, so it is closer. So, this profit is less than the profit of Stackelberg. So, in this case, if K1 is equal to output of this Stackelberg thing, then in stage 2, Cournot outcome is Q1 is equal to K1 is equal to this, and Q2 is this, because form 2 is going to, if this is the case, form 2 is going to earn a positive profit because Q1L is this point is the Q1 limit output of form 1. So, form 2 is entered. So, in this case form 2 enters, but if form 2 enters, it gets more profit than by deterring the entry of form 2. By deterring the entry of form 2, it gets less profits than by allowing the form 2 to enter and having capacity this much. So, in this case, so the optimal K1 is this and form 2 enters, and the outcome, Cournot outcome is K1 is equal to this and the profit this much, and you can see and the reaction function of form 1 is going to be this much, this one, and this is going to be the outcome. Okay. So, in case 3b, we see that form 1 accommodates the entry of form 2. So, here form 1 accommodates entry of form 2. Okay. Next, we look at this 3c, where we get a situation like this. Then this is, we do not know, So, suppose this is the this is Q1S, this is Q1S dot, and limit output is somewhere in between. Okay, and this is suppose V. Okay. Now here, if K1 is equal to Q1S, okay, limit output is here, right, then what is going to happen? Its profit is this, and here limit output is this much. So in this CA, reaction function limit output is at this point. So it is here, Stackelberg. So farm 2, this is going to be the A. So farm 2 enters, and if farm 2 enters, what is going to be the outcome? It is going to be K1 is, we have seen this, and this is the output of farm 1, and so is this Stackelberg. Profit is here. So at this point and this point, since they are in the same iso profit, so the profit is same. But if you compare this limit output and this, you will see this is greater than this. So if farm 2 suppose produces 0 output and farm 1 produces this, so this, the profit it gets is more than the Stackelberg thing. So at this point, this profit of farm 1 when it produces this and output of farm 2 is 0, this is greater than this Stackelberg. So we get it from why it is greater, because Q1 this is closer to Q1M than Q1S0. So this is closer to Q1M, and this is here Q1S0 and Q1A is this. So in this situation, if K1 is equal to K1L, then it deters the entry of farm 2, and the output is, in this situation we will get the reaction function. Suppose this is of farm 2, here this is this, then this thick line is going to be the reaction function, and it is going to produce here, not here, it is going to produce here. Outcome is going to be here in this here, because K1 is this, and this is, since it is left of this CA, so profit here is higher than the Stackelberg profit at this point. So it deters the entry of farm 2. So what do we get? We get that farm 1 can deter the entry of farm 2 in this situation, in case 3A, where Q1L is less than Q1M, and in case 3C, when Q1L is less than Q1S0, and this is So, this is the important thing. And in case tree B, when we have it, in this it deters farm 1, deters the entry of farm 2, here farm 1 accommodates the farm 1 accommodates the entry of farm 2. Okay. And we have seen in case 1 farm 1 deters, and in case 2, in all the cases we have seen A and B, it accommodates. So, these are the subgame perfect Nash equilibrium. In case 1, farm 1 deters, it is a blockaded monopoly. In case 2, it is always accommodates, because profit of farm 2 is positive both at point V and point T. In case 3, we get mixed outcome. In case 3A, when we have this situation, farm 1 deters. In case 3C, when we have this, that is limit output is less than this outcome, this output of farm 1, then farm 1 deters. But if limit output is greater than this, then farm 1 accommodates the entry of farm 2, and there is this Stackelberg outcome in Cournot competition. Okay. So, these are the outcomes that we get in this Dixit entry deterrence model. So, we see that farm 1 will not always deter the entry of farm 2, it sometimes it will accommodate, but in certain cases we see that it will deter the entry of. So, it is not a uniform thing to say that farm 1 will always want to deter the entry of farm 2. Okay. So, you can read this portion from chapter 14 of this book, Industrial Organization, a Strategic Approach, by Search and Where. So, these are the specific page numbers. Thank you.